Now we are in the differentiation and integration of power series. So when we say power series, we remember that it defines a function on its interval of convergence. So a natural question arises sometimes that can we perform calculus operations on this function, such as taking its derivative by operating on the power series itself? So the answer is yes. So under the right conditions, a power series can be differentiated term by term, just like a finite polynomial. So this is a powerful tool that allows us to find new power series representations from known ones. So just as we can differentiate a power series term by term, we can also integrate it term by term. So this provides a powerful method for finding power series representations for functions defined by integrals and for approximating definite integrals that are difficult or impossible to evaluate with elementary antiderivatives. So that is why we are now discussing on how to differentiate and integrate when involving power series. Now let's look at this theorem. So if the power series summation of c sub n multiplied to x minus 1 minus a raised to n has radius of convergence or greater than 0, then the function f defined by is f of x is equals to c sub 0 plus c sub 1 multiplied to x minus a plus c sub 2 x minus a raised to 2 plus is equals to c sub n is equals to x minus a raised to n, where n is equals to 0. So it is differentiable and therefore continuous on the interval a minus r or a plus r. And let's say the first derivative of f of x is equals to c sub 1 plus 2 c sub 2 multiplied to x minus a plus 3 c sub 3 x minus a multiplied to x minus a raised to 2 or x minus a squared continuous. So it equals to summation of n raised to c sub n, where n is the constant here, or the coefficient. So we have here x minus a raised to n minus 1. So in next is we have, let's say we have integral of f of x dx is equals to c plus c sub 0 multiplied to x minus a plus c sub 1 multiply to x minus a squared over 2 plus c sub 2 x minus a cubed over 3 and so on and so forth equals to c plus summation of c sub n x minus a n plus 1 over n plus 1 as n is equals to 0. The radii of convergence of the power series in equation 1 and equation 2 are both r. So in equation 1 and equation 2 in theorem 2 can be written in the form dx and integral. So important notes that the radius of convergence r of this new series is the same as the original, and the interval of convergence might differ at the endpoints, so they must be checked separately. So the index of the sum often changes to start from n is equals to 1 because the derivative of the constant n is equals to 0 terms is 0. Now let's have an example. So find a power series representation for the function f of x is equals to 1 over 1 minus x squared and state its radius of convergence. So for our solution, we will start with the known geometric series, which is 1 over 1 minus x is equals to the summation of x raised to n, where n is equals to 0. Now it is equals to 1 plus x plus x squared plus x cubed plus so on and so forth for the absolute value of x is less than 1. So we notice that 1 over 1 minus x squared is the derivative of 1 minus x. Therefore, we differentiate both sides of the equation. We can have now d over dx, or the derivative of 1 over 1 minus x, is equals to d over dx summation of x raised to n, as n is equals to 0. So the left side is d dx 1 over 1 minus x is equals to 1 over 1 minus x squared. So the right side is differentiated term by term. So we can have now the summation of d dx x raised to n is equals also to the summation of n x n minus 1. Since the n is equals to 0, term is 0, we can start that the summation, that sum from n equals to 1 is d n x raised to n minus 1. Therefore, we can have 1 over 1 minus x squared is equals to the summation of n x raised to n minus 1, as n is equals to 1, is equals to 1 plus 2x plus 3x squared plus 4x squared plus so on and so forth. Since the original series for the 1 over 1 minus x had radius of convergence r is equals to 1. So the differentiated series also has radius of convergence r is equals to 1. Another example that we have is to find a power series representation for arctan x and use it to approximate pi. So for our solution, we start with a known series. So let us recall the geometric series formula. We have 1 over 1 plus u is equals to summation of negative 1 raised to n, u raised to n, as n is equals to 0 for the absolute value of u less than 1. So let u is equals to x squared. Then we have 1 is equal over 1 plus x squared is equals to summation of negative 1 raised to n, x raised to 2 sub n, or 2n, as n is equals to 0 for the absolute value of x less than 1. So now we know that the derivative of arctan x is 1 over 1 plus x squared. So we integrate both sides. So we have now arctan x is equals to the integral of 1 over 1 plus x squared dx is equals to the integral of the summation of negative 1 raised to n times x raised to 2n dx. Integrating it term by term, we have now arctan x is equals to c plus summation of negative 1 raised to n. So we replace x raised to 2n. So we have now x 2n raised to 2n plus 1 over 2n plus 1 is equals to c plus x minus x cubed over 3 plus x to the 5th over 5 minus x raised to 7 over 7, so on so forth. So to find the constant c, let x is equals to 0. So we have now arctan 0 is equals to c plus 0 minus 0 plus 0, so on so forth. So 0 is equals to c. Thus, the power series for arctan x is arctangent x is equals to summation of negative 1n multiplied to x raised to 2n plus 1 over 2n plus 1 is equals to x. As we integrate it, for the rule of integration, we did this. So we have now x minus x to the cube over 3 plus x to the 5th over 5 minus x to the 7 over 7 by the integral rule. So on so forth. So the absolute value x is less than 1. This series also converges as at x is equals to positive negative 1 by the alternating series. So now since arctangent 1 is equals to pi over 4, we can substitute x is equals to 1 into the series. So we have pi over 4 is equals to 1 minus 1 third plus 1 fifth minus 1 to the 7 plus 1 9. So on so forth. So multiplying by 4 gives the famous Gregory-Leibniz series for pi. So we have pi times is equals to 4. We have now 4 multiplied to 1 minus 1 third plus 1 fifth minus 1 over 7 plus 1 over 9 minus so on and so forth. So this series converges very slowly, but it is a classic example of using power series to represent fundamental constant. So that is the examples that we have for our differentiation and integration of the power series. And that's all. Thank you.